All right, again, thank you, Laura. I want to thank SPIE for this opportunity. And I know a lot of my friends are out there watching. I want to say hi to you, all the students I've had from the University of Arizona, University of Alabama, Huntsville, and SPIE short courses. Again, I'm optical technologist at Meta. I'm involved in virtual reality optical engineering, but I spent the last 20 years as a professor at Optical Sciences. I am emeritus professor there. You can still reach me at my Arizona address. I also want to acknowledge Karam Young and Tiffany Lamb, who co-authored my textbook with me, for a lot of help in what I'm going to show here. On Sunday, August 20th, I'm teaching a short course, Polarized Light and Optical Systems at the San Diego Optics and Photonics. And so what I'm going to do here is I'm going to give some high points from that short course, so you get an idea what the short course is about. And the course talks about polarization effects in optical systems and how polarization aberrations adversely affect metrics for optic systems. The short course follows my textbook, Polarized Light and Optical Systems, which was published by CRC Press in 2018. But that's a class for undergraduate, graduate students that was developed for over 20 years at the College of Optical Sciences. And a lot of the figures that you're going to see here were produced with the Polarism polarization ray tracing program and or Mathematica. Polarism is a polarization ray tracing optical analysis program from Area Optics in Tucson. And just this disclosure, I'm a part owner of Area Optics. But the textbook, the first third of the textbook, covers polarization calculus and how we do polarization calculations before getting into ray tracing and aberrations around chapter 10. And the next part of the book is then how we do the ray tracing, the real mechanics of it, calculating polarization aberration. And the last part of the book talks about the different models that we have in polarization optical design: anisotropic materials, uniaxial materials, crystal polarizers, gratings, holograms, liquid crystal cells, stress-induced birefringence, and the like. And so again, I'm going to show results from the Polarism, also from the AXIScan Mueller matrix polarimeter. And Polarism is from Area Optics, which, disclosure, I was a founder of. And AXIScans come from Aximetrics in Huntsville, Alabama, where I was an investor and helped get that company started. Also, I'm an employee of Meta, but all of this material expresses my views and my opinions. So none of this is indicative of Meta's work or Meta's plans. In fact, it was prepared prior to my employment with Meta. I'm going to assume some polarization fundamentals here so that we can get right into some really interesting things on polarization aberrations. And obviously, you can find background in that first third of my textbook. So, can't quite see the top of my screen here. There, polarization engineering. For many optical systems, selecting good combinations of polarization elements can be difficult. You know, some systems require many years of dedicated polarization engineering, and we would call these polarization critical optical systems. They have specifications which are difficult to meet. Examples are liquid crystal displays, optics for microlithography. And so polarization engineering is the task of designing, fabricating, testing, and often mass producing with high yield such polarization dependent optical systems. For example, here are two good examples. For polarizers, we have angle dependence. The extinction of polarizers is very high when the angle of incidence varies parallel to the transmission axis or perpendicular to the transmission axis. So here I have a green polarizer indicated in front and a red polarizer indicated in back with horizontal lines. And you can see from the normal, as we look from the side, these remain orthogonal to each other. But when we go off axis at 45 degrees, even though this is along X and this is along Y, they no longer appear orthogonal at a 45-degree angle. And in fact, light will leak through. It'll be polarized by the first polarizer, but it won't be orthogonal to the second polarizer. And so we get leakage in the diagonals of the field of view of a polarizer as a function of angle of incidence. And we have many ways to fix this. You can go look in the path literature, find a half a dozen, fixes for this with C plates and half wave plates and the like. Another problem is the wavelength and angle dependence of birefringent retarders. Here I show for a quarter wave at 600 nanometers, how the retardance of mag fluoride and quartz vary across the visible. These are the two most common retardant materials for the visible. And I can create combinations of them like an achromatic lens to make an achromatic retarder. But it's a fundamental issue that we have this significant wavelength variation. In addition, as a function of angle of incidence, because of the differing path length going through an element as we go off axis, and because for crystals, this will split into ordinary and extraordinary refractive indices, we find for birefringent retarders that when we tilt along the one axis, the retardance increases quadratically. When we tilt along the orthogonal axis, the retardance decreases quadratically. And there are some axes here around the diagonals where the retardance is close to constant. So we see that our polarizers are imperfect. They have aberrations. Our retarders are imperfect. They have aberrations. And so we would define polarization aberration as deviations in an optical system from the desired polarization state or the desired polarization properties. So for example, I might want a circularly polarized beam like this one here on the top. Okay, well, here we see a spatially varying polarization that might be coming out of one optical system where it's become elongated or elliptical, in the tangential direction going around. So here it's vertically polarized, here it's horizontally polarized, and the like. And so here we have a quadratic variation that's tangential. Here there's a variation from horizontal through circular to vertical elliptically polarized. It's linear and going vertically. Or here's another quadratic example, but in this case, the variation is radial. And so if this isn't what I want, this is an aberration. And to change the light's polarization, I have to change the light's interactions. I can't just change the light itself. I've got to put in something that retards or polarizes to alter the polarization state. And so we can use polarization ray tracing to supplement standard ray tracing algorithms, but use calculations to follow the evolution of the polarization state through the optical system and determine the polarization properties of ray paths. And so, for example, here are 2 or 3 terms in a polarization aberration expansion. I can have a constant polarization effect. I can have a linear effect. Here going from vertical to horizontal across the x-axis, or 45 to 135 across the y-axis. So this is linear through the origin in every direction. I can have quadratic effects, okay? But you notice that I've drawn these with lines, okay? Because we're talking about polarization, and that polarization can be diattenuation, just like a weak polarizer, or can be retardance. Okay, so wavefront aberrations are scalar. So piston is just a constant, tilt is a linear variation, defocus is a quadratic variation. But if I have diattenuation and retardance, I have an orientation, a fast axis for a retarder or a transmission axis for the polarizer. And then I have a difference, an amount of the retardance or an amount of the diattenuation. So corresponding to piston, tilt, and defocus, the corresponding polarization variations can be mapped out, with these 3 examples here: a piston retardance, for example, a tilt retardance, for example, a defocus retardance. And then when we go through an optical system, we're going to encounter a series of polarization elements or interfaces that will be polarizing. And so when I get to the first ray intercept, there's a Jones matrix for that. And there's an altered state that exits. When that altered state gets to the second ray intercept, it has a Jones matrix and exits and so on. So as I propagate through an optical system, if I can write a Jones matrix for the first, second, third, fourth ray intercepts and multiply these together, I can get the polarization properties for a array through an optical system. So this is the basic concept for polarization ray tracing. I have a sequence of polarization effects. I have a sequence of polarization matrices. And so our objective in polarization ray tracing is to calculate the evolution of polarization state through an optical system. And here I just show, for example, like a DVD player that has lenses, spatial filters, apertures, a quarter wave plate, mirror. Actually, this is an polarizing interferometer, a mirror, and the like. And so we can write Jones matrices for every ray intercept and then get the dye attenuation, the retardance associated with the ray paths through the optical system, and assess the impact of the polarization aberration on the image formation. And then if these are important, we need to be able to confirm that. And so this is done with Mueller matrix polarimeters. These are used to test polarization elements, and they can also be configured to test the polarization of ray paths through optical systems. And so here we see a head, light is coming in the fiber from the spectrometer, and there's a beam splitter here to pick off a reference beam, but a polarizer and a spinning retarder give a rapidly varying polarization state on a sample that can be clipped here onto this platen. The sample will change the polarization as a Mueller matrix, it's a dye attenuator or retarder, and another more rapidly spinning retarder and fixed polarizer down here create a modulated signal that we can then decode into the sample's Mueller matrix. And from that Mueller matrix, we can get the sample's dye attenuation, retardance, and depolarization. And then when we're characterizing elements, we often want to rotate them to characterize them as a function of angle of incidence. So here's a 2-axis rotation stage. This is changing the angle of incidence, and then this rotates to change the azimuth. Here's one configured for XY testing. So it's just going to translate the sample back and forth. And these are used in factories where they produce polarizing films or liquid crystal cells or displays when they set up the manufacture of liquid crystal displays and when they do the ongoing quality control. Here's just an example of a defect in a liquid crystal compensating film, type of data that we would use. And then I can take one of these polarimeters and I can mount these heads on motors, and I can swing the polarization generator around to send different light rays into an optical system. I can swing the polarization analyzer around to track the exiting beam. And on a ray by ray basis and a wavelength basis, I can map out the Mueller matrix for ray paths through an optical system and compare that, for example, against simulations or specifications. So I'm now going to look at a couple examples of polarization ray trace and the type of information that we use. And these are examples that have been taken from the short course. So I dwell on these in a lot more detail if you've taken the class or if you meet up with me in San Diego on August 20th. Okay. One last thing I'll mention is because we're ray tracing, light is constantly changing direction. So one of the examples we're going to look at is light reflecting here from the z-axis to the y-axis off a mirror, off a second mirror into the x-axis, and off a third mirror back into the initial z-axis. So it's entering and exiting in the same direction, but we have these 3 reflections, and we're going to take a converging beam and look at it. Here we can see that 45-degree polarized light becomes elliptically polarized by the retardance of an aluminum mirror. Its axis is also rotated a little by the dye attenuation. But here, if the second mirror is at the exact same angle, these will cancel for that one on-axis ray. So it's back to 45 degrees. Then the third mirror converts it back to elliptically polarized light again. And so I can write a Jones matrix for these 3 and keep track of the coordinate changes. But we find it very convenient to go from the Jones matrix formalism into a 3 by 3 polarization ray tracing formalism. And so we can describe the light's polarization with a 3-element vector. And then for each reflection, refraction, polarizer, retarder, or the like, we can use a 3x3 matrix to describe the polarization interaction. And the ray tracing program has to have subroutines that contain all the physics for these interactions. And we have 3 properties, 2 of which we're most concerned with, and then a third for completeness here. But diattenuation is when we have a polarization dependent amplitude change, like polarizers. This is also like just what happens at Fresnel reflection or refraction from air to glass interfaces. Retardance is when we have a polarization dependent phase change, shown down here. Because of the optical axis of this crystal, there's a different polarization state for the vertically polarized and horizontally polarized modes have different refractive indices and exit with different phases. And then depolarization, which is a random reduction in the degree of polarization. It's usually associated with scattering, bubbles, cracks in my lens and my coating peeling off. Usually this is not a particular problem in a high quality optical system. And so in ray tracing, we have a geometric ray trace where we calculate a series of ray intercepts. Here's a fan of rays intercepting this first, second, and this third mirror. Okay. And then from that set of ray intercepts and the refractive indices in each of the spaces, we calculate the optical path length from an entrance pupil to an exit pupil, and we can calculate the wavefront through an optical system. And so the principal objective of ray tracing is to get this wavefront aberration function. And then when I have the wavefront aberration function, I can calculate point spread functions, optical transfer functions, and the like. If these are 3 aluminum mirrors, though, they also contribute their own S&P phase change, which can be calculated from the Fresnel coefficients for aluminum. And here I just show that if you do this ray trace for um, a beam here, we actually get a additional tilt over the geometrical optical path length. And this is a calculation of the polarization effect from the contributions of the phase shifts from these 3 mirrors. So let's dig into this a little more. In a polarization ray trace, we have to do this geometric ray trace and calculate all the ray intercepts and all the optical path lengths for each ray segment. Then we're going to calculate the surface normal at the ray intercept so we can calculate the reflected and refracted propagation vectors. And then we will calculate the S&P basis vectors for the in-plane and perpendicular plane of incidence polarization components. We have to get matrices to rotate our original light into this S&P coordinate basis, and then we calculate the amplitude coefficients for that particular interface. These are Fresnel coefficients. If you're uncoated, we use thin film programs. If it's a coated interface, we use rigorous couple wave analysis. If it's a diffraction grading or similar mathematics, if it's a hologram. And one of the more complicated cases is we have to do anisotropic boundary value Maxwell calculations for crystal optics. But after getting these amplitude coefficients, we know how the S and the P polarization change. We can write this polarization ray tracing matrix and just keep track of how our coordinate system is changing. And then we have to repeat this going through the system from the first to the second to the third intercept. So for example, for this ray at 45 degrees, propagating down the z-axis, the first ray intercept has this 3x3 matrix, the second has this, the third has this, and then I can repeat this calculation over my grid of rays and, for example, calculate the effect of the aluminum mirror on my wavefront in addition to the geometrical optics. And so when I repeat this, I end up with a polarization aberration function over a grid of rays over the exit pupil. Here I've just padded this with zeros to represent rays that are outside my aperture, but each one of these comprises a polarization ray trace from object space to image space, and this describes the change of polarization in 3 dimensions. Then we find it helpful to flatten this out back into a Jones matrix, and we call this Jones matrix the Jones pupil. So now I have written a wavefront aberration function made up of Jones matrices, and this shows the amplitudes of the Jones matrices for this three mirror system, for example. And it's got an amplitude part. It also has a phase part shown over here. And so now I can send in an arbitrary Jones vector in object space. It rotates some polarizer, creates some particular incident polarization state. And by multiplying on a ray by ray basis, that incident polarization state by its Jones matrix, I can get the exiting polarization, which will have X and Y components in amplitude and phase. And this will tell me how the exit pupil will be apodized for different polarization states. And this will tell me how the phase changes for different polarization states in the exit pupil. So these would be contributions to the interferograms that I would measure for the optical system. So let's consider a more interesting coating than just a bare aluminum coating. One common type of coating is a high reflection coating made out of many quarter wave stacks. So if I have an uncoated interface of glass with 4% reflection, if I put a high and low layer down of like 1.8 and 1.38, like hafnia and magnesium oxide, I can get the reflectance up to over 25%. 4 layers, I'm over 50%. 6 layers, I'm over 70%. And by 18 layers, I'm up almost to 100% reflectance. And there's essentially no light getting through. And then that's this black curve here. And this is showing us a function of wavelength. I designed this at 550 nanometers, but as I increase or decrease wavelength, I'm no longer a quarter wave at these wavelengths. And so eventually I move off the top of this bandpass of this high reflection, and my reflection falls off. If I then go to 30 degrees angle of incidence, that's the well-known blue shift of bandpass filters, interference filters in general. And so we see that the S and the P have shifted towards shorter wavelengths. And because the Fresnel coefficients in each interface are different for S and P, we find that the peak band pass has become narrower than the S band pass. They're both still highly reflecting, but that reflection has shifted to a shorter wavelength. So I want to take a coating like this, optimized for 800 nanometers, and this shows the Fresnel coefficients for that coating at 0 and 30 degrees. So these are the intensity coefficients for RS and RP and TS and TP. And we get this very high S reflectance out here at larger angles, but it falls off around 45 degrees. And so this shows how the dye attenuation varies as a function of angle of incidence. And then this shows how the retardance varies as a function of angle of incidence. So now I have a lot of polarization effects, so I can make a really interesting example out of this 3 mirrors. So we can have a little fun looking at the results of a polarization ray trace calculation. So first, I've got the 3 mirrors. So I'm going to have an angle of incidence at the first mirror, the second mirror, and the third mirror, and we'll compare the aluminum and the high reflectance coating. And so the angle of incidence is the same at the first mirror and the second mirror and the third mirror. So that's what's shown here. And then we can map the dye attenuation. And this shows for the aluminum mirror that there's less dye attenuation at smaller angles of incidence, more dye attenuation at larger angles of incidence, and it's rotated because of the different orientations of the 3 mirrors. And so cumulatively, this is the dye attenuation after the first mirror. This is the dye attenuation after the second mirror. And we saw before that for that on-axis ray, its angle of incidence was 45, S became P and P became S. So there's no diattenuation at the very center. And then the color here indicates the magnitude of the retardance, and the lines indicate the orientation. And after the third mirror, we have this. So this is the exiting diattenuation for the aluminum mirror. And the magnitude down here is that we have reached a maximum of about 0.25 diattenuation for this beam here, numerical aperture of about 0.7. For the bandpass coating, we've got a similar form to the diattenuation, but now the magnitude is much, much greater. Here, after the second mirror, our diattenuation magnitude gets up to almost 80%. And then this is the diattenuation from front to back. And we have a complete different orientation of polarization about this line here where the diattenuation tended to cancel. So the purple here is a minimum diattenuation, and then it's growing towards the left side and towards the bottom. Similarly, this is the retardance for the 3 aluminum mirrors. Again, after 2 mirrors, the retardance cancels here in the center of the pupil. But after 3 mirrors, I have this retardance distribution, which has retardance up to about 0.4 radians of retardance, which is about 24 degrees, which is still less than 1/10 of a wave of retardance there. But for the bandpass coating, I've got almost 1 wave of retardance. Here I've got 3 radians of retardance, and we see the retardance accumulating from the first to the second to the third mirror. So I've got these enormous polarization effects by going to this bandpass filter, but moving off the bandpass into a wave band where it's not very good, chosen for example. And so I can write the Jones pupil for the aluminum, okay? And because of the 3 rotations, I ended up with X polarized light after 3 reflections coming out as Y and Y coming out as X. So these off-diagonal elements are the largest, and these elements are quite small, around 0.1 or so. But for the bandpass coating, I've got this very curious Jones pupil, and I'm just showing the amplitude here. Okay, so it's highly apodized, and it's just darn interesting. So if we look at the point spread function that we can get by Fourier transforming the light in the exit pupil, if we take light incident at 45 degrees, after 3 reflections from the aluminum, it comes out at about 135 degrees. And so here I have a point spread function, and I've shown the polarization state at every point in the point spread function with an ellipse. So it doesn't vary that much, okay? So it's close to an airy disk, and it's slightly elliptically polarized. And here I have increased the scale, so I've just zeroed out the center. You can see what the polarization is doing out in the diffraction rings here with these ellipses. By contrast, when we took the bandpass coating and we detuned it off its transmission band and sent in 45-degree polarized light, because of the large diattenuation and retardance aberrations, the point spread function has a large amount of variation. Okay, not only that, it's shifted because we've picked up a considerable amount of tilt in the phase coming out. And so we see here horizontal polarized light at the top, 45-degree polarized light in this corner, vertically polarized light in this corner. And so the polarization aberration in our exit pupil similarly caused a large polarization aberration in our point spread function. And here again, if we look in the diffraction rings, we can see the polarization has significant variation out in the diffraction rings. as well. So this gets very interesting. And so here we show if we send in horizontal polarized light in the exit pupil, these are the polarization ellipses, which are all close to vertical. The arrows indicate the phase. There's a bunch of wavefront aberration. But the case we just looked at was the 45-degree polarized light. And there, one side of the pupil is vertical, one side of the pupil is horizontal, another side of the pupil is at 45 degrees. And so we get this huge spatial variation in polarization coming from vertical dye attenuation, horizontal dye attenuation, 45-degree dye attenuation. And then vertical polarized light, again, there's a lot of change in amplitude, but there's not so much change in polarization. It's sort of near an eigenstate of the net properties of those ray paths. So this showed the point spread function for a single polarization state, 45 degrees, but it's well known that the point spread function itself can be written as a Jones matrix. And that Jones matrix we call the amplitude response matrix. So like we have an amplitude point spread function and an intensity point spread function, which is usually just called the PSF. So this is the amplitude point spread function for the aluminum. Okay, and these two values here are large, they're around 0.8. This is a small value around 0.4, but you can see that the aluminum couples some light into other polarizations, and that light is not as well behaved or as well focused here. But for the case of this bandpass coating, where we have the large diagonal components, now we see sort of astigmatism in different directions. These component of the point spread functions in a different location than these. They've been shifted because there's different phase shifts between the X and the Y polarization. And there's a lot more light coupled into these other elements of the Jones matrix. So then the way that we can take this amplitude response matrix is we can multiply this by a given Jones vector, and that will give us the Jones vector of the image. So when we multiply this by 1, 1 for 45-degree polarized light, we get an X amplitude in phase and a Y amplitude in phase. And that's where this point spread function was calculated, represented by a bunch of ellipses. Each point here has an X amplitude, an X phase, a Y amplitude, and a Y phase. But for every different incident polarization state, we're going to get a different point spread function. And so that's all contained within this Jones matrix. We can then convert these Jones matrices into Mueller matrices, and this will give us the Mueller matrix we would measure in the exit pupil. So this is what we usually measure with these Mueller matrix polarimeters. I can shine in a grid of rays at different angles and different positions into the optical system, measure the Mueller matrix of the corresponding exiting ray. So we just sweep the incident, sweep the exiting, build up a Mueller matrix pupil. And that's what we've done here for the bandpass coating as well. Similarly, we can take this amplitude response matrix and convert it into a Mueller matrix, a Jones matrix to Mueller matrix conversion. And that will give us a Mueller matrix point spread function. So this is an example of a polarization ray trace where we took into account Fresnel equations for aluminum or multi-layer coating equations for a bandpass filter. I'd like to show one more example of stress birefringence in lenses. Okay, so now we use a lot of injection molded lenses because they're cheap, in consumer optics, and we can make aspherics. But because of the injection molding process, there's inevitably stress that remains in these elements after molding. So here we show the lens between cross polarizers. It's dark across here X, dark across Y, but there's light leaking through the corners because of the distribution of stress in the lens. We also see a lot of stress around the gate, which is where the plastic is injected, and generally there's higher pressure and larger temperature variations there during the molding process. And now if we rotate this lens by 45 degrees, we can see the gate has moved over here. Most of the pattern has stayed the same because it's generally due to compression on the front and back surfaces of the lens, but we can see it. Here's just an example of stressed birefringence where there's a microscope slide held with 3 pins, and there's a force being applied here, and we can see between cross polarizers polarization change that has resulted in this piece of glass. Or here's a piece of glass that was cooled rapidly, so it was never annealed. And this is what can happen if we don't anneal our glass, is that we can have large pent-up stresses that remain inside the glass. So in injection molding, we use finite element programs to simulate the injection molding process. And so you can assign a temperature to a mold and the shapes to the mold, and then flow a viscous fluid into the mold, and step by step watch it fill the mold, apply pressure, to completely fill the mold, and then step through time while the heat flows out through the mold and the element solidifies with these stresses inside. And the result of that is we have a CAD file that has an array of stress tensors, each that has 6 stress coefficients. And so I have a number of points where the finite element program has calculated the stress. When I'm doing a ray trace, I can calculate the incident and exiting ray locations, and then divide this up, for example, into like 100 different segments. And for each of those segments, I can look at the neighboring points in the file to calculate what is the retardance and what would the polarization matrix be for each of these ray segments. And each of these ray segments is going to vary because of this stress distribution. So this is an example of one of these stress calculations from a program called Time in 3D, which is common in Asia. There's another program from Autodesk called MoldFlow, which produces very similar output. And here you can see the compression on the outer surfaces of the lens, some tension here in the center of the lens. This is natural because lenses tend to cool from the outside, and then the inside cools later. And so the outside compresses and that pulls on the inside. And this particular lens is like 10, 12 megapascals. But we can calculate this for each ray based on a stress calculation, and then perform a ray trace and update the polarization information we would get from the surfaces and coatings with the polarization information propagating through the lens. And so here's that lens that just shows a cross section through the lens showing stress distribution. And if we had no stress, then we would have a point spread function that would be close to the airy disk. And that's what we see in here with this red. This is a log of that point spread function. And this is close to the identity matrix. So if there's no stress, there'd be very little polarization change. There's a small amount here from the Fresnel refraction into and out of the lens. If we then take the stress that we calculated and apply that, now we see that there's more light in these off-diagonal elements, and that there, if you were to look closely, you would see that the quality of this image and its Strel ratio has decreased. But for this level of stress, this is still a very acceptable point spread function, which is what we wanted to know. Because this is a simulation, I can put in 10 times the stress. And so here with 10 times the stress, now we see more than 10 times the light coupled into other polarization states. We see a lot of astigmatism showing up, a lot more light in the diffraction rings. At 100 times the stress, well, I have an image, but it's a big blurry image. And at 1,000 times the stress, I just get a speckle pattern. because there's so much variation of polarization and phase. It's become more a random screen than a lens. But here you can see how we can use polarization ray tracing to simulate stress birefringence. In the short course, we'll talk about calculating the polarization effects of crystals. We can use this for Glan-Thompson, Glan-Taylor polarizing prisms, for wave plates, for the like. We also integrate rigorous couple wave analysis, so we can include diffraction gratings in our simulations. And we have methods of using the Baraman calculus for biaxial multilayers for simulating some of the polarizing films that we use, as well as liquid crystal cells. But in summary, polarization ray tracing simulates the diattenuation and retardance aberrations of optical systems. The wavefront aberration function, the point spread function, the optical transfer function all become polarization dependent. And we use Mueller matrix polarimetry, among other polarization tests, to measure the polarization of ray paths through optical systems to confirm that we have reasonable models, or that we're building the system that we need to build. So that's the end of my prepared presentation, and I went through this a lot faster than I would like to. So I hope that if you haven't seen my short course, I'll see you in San Diego, and we can dig into this and into detail. But I'd love to take some questions on this material, so please.
Thank you so much, Russell, for that excellent presentation. A lot of information packed in here. And we have quite a few questions that have come in. So in the interest of time, so that we can get to as many questions as possible, I'm going to be reading them to you, Russell. I apologize in advance. I will read the names of the participants that are asking. I apologize in advance if I have messed up your name. And then I will also be reading your questions and some of these technical words to the best of my ability. So apologies for any mispronunciations. Don Nicholson has asked, if it is necessary, how do you confirm perfection in construction of the mirror?
So perfection in the mirror would be if it matched the calculated thin film properties from a program. So it might be a bare aluminum or silver mirror, or some multi-layer coated mirror like I showed. And so normally we would use polarimeters or ellipsometers to map the polarization and make sure that it had the right coating and it was performing the desired polarization transformations. So it's just digging into the polarization metrology.
Thanks, sir. Another question here from Don Silberman. Have you or might you work on polarization of metasurfaces for AR/VR systems?
Well, there's a lot of work on that, and I don't want to talk about my own work, but these methods directly generalize to metasurfaces. And so we can write a Jones matrix, a polarization ray tracing matrix for a metasurface. We may have to do it for several diffraction orders if they're significant, but the general formalism presented here works fine for metasurfaces, but you have to program up the metasurface amplitude coefficient calculation through rigorous couple wave analysis or finite difference time domain or some appropriate algorithm to get a Jones matrix.
Okay. Another question here from Stefan Richter. Two questions on the polarization ray tracing. First question is, can it be extended for situations of partial propagation through anisotropic media, maybe even anisotropic and absorptive? I'm wondering about how to treat wavefront being not parallel to the ray pointing vector.
Yes, so in the short course, I have a long section on doing crystal optics, anisotropic material polarization ray tracing. Because rays split into ordinary and extraordinary modes in uniaxial crystals, we get two different K vectors and pointing vectors and 2 different rays through the rest of the optical system. So from that point forward, you have to treat it as 2 rays. There may be a second anisotropic material that'll generate 4 rays, and so on. And so we have to have a Maxwell equation solver to give us the Fresnel coefficients and all of the electric and magnetic fields associated with the ray intercept. And it's a lot of work, but it's in the polarization ray tracing program. And in the short course, I go through some examples of Glan-Taylor, Glan-Thompson polarizers and show, practical examples of doing this.
And Stefan's second question is, what about multiple reflections? An example structure for both questions would be a wedge made of a monoclinic material.
Right. So if it's outside the coherence length, I'm going to treat it as multiple rays. If it's inside the coherence length, I'm going to treat it, locally as a interferometer, as a multi-layer stack. So it tends to fall into one of those 2 regimes. But the basic methods here, you just have to write the right, macros and then perform the simulation.
We have another question here from Don Silverman. Have you or might you work on polarization effects in photonic integrated circuits, especially when considering quantum interferometers?
I'm sure there's people simulating this. And when we get into waveguides, we're generally using waveguide propagation algorithms. And so that's quite different than the polarization ray tracing that I'm talking about here. So I would only casually talk about that in the short course, but it's a really important subject. But that's outside, the areas that I've spent my career working.
Thanks, Russell. Veronica Mietes Alonso also has a question. She's wanted to thank you for your presentation and also ask if there's any Zernike-like polynomials to approximate polarization aberrations, or if it can only be done via polarization ray tracing.
I think that's a fantastic question. And that's a question that I asked myself when I was a grad student writing my dissertation, which is called Polarization Aberrations, because I did a lot of polarization ray tracing and I very quickly filled up my hard disk with numbers, Jones matrices and Mueller matrices, and I wanted to make sense of those numbers. And so at the beginning of this, I showed 3 polarization aberrations: piston, tilt, and defocus. But if you go into my textbook in chapter 15, yes, we continue these aberrations to higher order. And because of the nature of dye attenuation and retardants, they're not scalars. So we use vector forms of the Zernike polynomials to analyze these polarization aberrations. And so there's a whole zoo of retardance aberrations and dye attenuation aberrations that are well described by these vector Zernike polynomials. And that's a really fun subject.
So, Nuno Edgar Nunez Fernandez also has a question. His question is, how would polarization matrices change with metamaterials with changing refractive indices? Indices, thank you.
Yeah, so the basic thought process here is if we can treat, the light propagating through a system by rays, which isn't a great approximation for the waveguide question earlier, then we're thinking about those rays as having a series of Jones matrices that we're going to multiply together, or the 3-dimensional variant, the polarization ray tracing matrices. So if I change the refractive index, I'm not changing the S&P coefficients, but I am changing the strength of the interaction. And so the retardance and dye attenuation are going to increase or decrease. And so in the simulation, when we call the subroutine that calculates these amplitude coefficients, we're going to be able to play with the refractive index and study its effect. And with these aberrations, if I don't like my aberrations, then I want to find a way to reduce my aberrations, which is a little beyond the 40 minutes here. But then I have to look at what can I adjust to reduce or cancel aberrations across different parts of the optical system to meet a specification or get the best performance possible. And playing with refractive indices, like you asked, is an important part of the optical engineers' thorough investigation of an optical system.
Harshvardhan has a question. In Poincare sphere, at the center light is unpolarized. How can we explain mathematically by using Stokes parameters, and why is there evolution of SOP? I think it's state of polarization in Poincare sphere.
So when we're dealing with polychromatic light, light of multiple wavelengths, different wavelengths can have different polarization states. It's quite common. We just showed earlier how a retarder has different retardants for different wavelengths. And so to get unpolarized light, I have to have an averaging over wavelength or over angle of my polarization ellipses that cancels out any tendency for a given polarization state. And so unpolarized light doesn't occur for monochromatic light because monochromatic light is periodic. It's a cancellation of polarization components of different components of the light, either in wavelength, in space, or in time.
Jose Mendina's question is, what is your opinion about those jewel beetles in biology producing strong LH and or RH circular polarization and striking color effects? Also, why isn't circular polarization so common in nature?
So circular polarization is not that common in nature. Those beetles are really cool, and Michelson, of the famous Michelson-Morley experiment, I think was the first who noticed that these shells had circular dichroism, which can be explained by looking at I think it's chitin as the protein, but it rotates layer by layer and has a different absorption for right and left circular polarized light. So yeah, many of my friends have collections of those beetles. I've just admired their collections, but it's really striking. When we look at scattering, most scattering tends to reflect more S-polarized light, transmit more P-polarized light. And so when we scatter from natural materials, even from the atmosphere, there's not much circular polarization. It tends to be 0.1%, One exception is if you get to very narrow spectral bandwidths, like hundreds of a nanometer, and a certain, absorption and emission lines in the sun are magnetically active, and due to Zeeman splitting, we do get circular and elliptical polarization in sunlight around certain spectral lines from iron, chromium, nickel, and other atoms, but that gets averaged out because you have right circular polarized light, and a couple hundreds of a nanometer away, you have left circular polarized light, and the light that comes from the sun itself is almost entirely unpolarized unless you look at such a fine level.
Thanks, Russell. Looks like we have just a few minutes left here. So unfortunately, we're not going to be able to get to everyone's questions. Thank you so much for submitting them. I'm going to probably do a couple more here. The next one is from an anonymous attendee. And the question is, how does the interaction between polarized light and materials with different optical properties impact the design and performance of optical systems?
So we have so many kinds of optical systems. In interferometers, it's very useful to match the polarization state of the two beams that we're interfering, because when we have orthogonal polarization states, the intensity fringes vanish. So in interferometers, we work to match polarization state. In like instruments that observe the Earth from space, They want to accurately measure the color of the light scattered from the Earth. And so they remove polarization dependence of gratings and polarization dependence of fold mirrors, like I was showing here, with depolarizers, pseudo depolarizers. In microlithography, you want to get the absolute pristine best point spread function that you can, and any retardance or dye attenuation in the lenses is, as we saw here, polarization aberration detracts from the ideal point spread function. And so extensive work goes into all microlithography systems to control polarization of the surfaces. And then we have things like the liquid crystal displays on our phones and projectors and laptop computers, where we have very commonly, if it's not an OLED, but a liquid crystal display, there's a polarizer, an adjustable retarder, which is the liquid crystal cell, some compensating polarizing films to get a good angle of incidence dependence, and another polarizer. And so, again, there's an enormous amount of polarization engineering and polarization ingenuity that goes into all of these. And you can find many, many patents on all of these subjects. They're showing different people's inventions and just intrinsic cleverness in addressing this problem.